So hello everyone. Welcome to the course Topics in Locally Conformally Kähler Geometry. I would like to thank the organizers of this Geometry and Topology Summer School, especially Professor Mustafa Kalafat for the kind invitation. Unfortunately, I am not able to deliver this course online, so I will have to pre-record the lectures. But feel free to ask me any questions via email. So I will start by saying the plan of the course. Let me share the screen first. So the plan of the course would be the following. I will give an introduction to locally conformally Kähler geometry, some preliminaries, and some motivation for this topic. I will focus on many examples of locally conformally Kähler manifolds, especially in complex dimension 2, but also in complex dimension higher complex dimension, so at least 3. And I will spend quite a while to describe the geometric properties of locally conformally Kähler manifolds. Focusing especially on Weismann manifolds. Okay, so this would be the outline of the course, and I will start by fixing some notations. That I'm sure you are very familiar with already. So MJ will denote a complex manifold. J stands for the complex structure. So J is an endomorphism of the tangent bundle with the property that J squared is minus the identity. So this is an almost complex structure. Just the fact that the J composed with J is minus the identity, but being a complex structure, it means that it also satisfies some integrability condition. Which is encoded in the vanishing of a tensor called the Nienhuis tensor. So by this integrability condition, I mean that this relation is always satisfied. So this is also known as the vanishing of Nienhuis tensor. Okay, so this endomorphism of Tm is a complex structure, and it encodes all the information of a holomorphic atlas on the manifold M. Okay, we will denote, we will call a Riemannian metric Hermitian if it is compatible with this complex structure. So a Riemannian metric G is called Hermitian if it is compatible with J in the sense that G preserves J. So G of Jx, Jy equals G of X and Y for any X and Y vector fields. So Hermitian metrics always exist on complex manifold. This would be the first observation. There is no obstruction to their existence. So Hermitian metrics always exist. Because we can average somehow any Riemannian metric to transform it into a Hermitian one in the following way. So for any G0 Riemannian metric, we can define G0 tilde to be the metric given by G0 of xy plus G0 of jx, jy. So this new metric G0 tilde has the property that it is compatible with J, just by this definition. Okay, so this is Hermitian. The second observation, second remark, is that out of a Hermitian metric and a complex structure, we can cook up a two form that is called the fundamental form of the metric. So G Hermitian plus J complex structure will produce a two form omega in the following way. So omega applied to X and Y, two vector fields, is by definition G twisted with J on the first component. So G of J, X, and Y. Omega thus defined is a skew symmetric to tensor. So it is a two form. That has two important properties. So first of all, it is a 1-1 form in the sense that it preserves J. So this means it is a 1-1 form. And omega is positive. The positivity coming from the fact that G is a metric. So omega is positive, meaning that omega applied to X and Jx is strictly greater than 0. It's a positive number. Okay, so as I said, omega defined in such a way is called the fundamental form of the metric G. Usually in complex geometry, we won't make any difference between G and omega. So we will refer often to omega as being the Hermitian metric. So this is the first remark, that G or omega are both referred to as being a Hermitian metric. And the reason is that out of these three elements, G, J, and omega, we need only two to completely determine the third one. So out of G and J, we can easily recover omega, and the same out of omega in J, we can recover G, and out of omega G, we can recover J. Okay, this fundamental form, or this Hermitian metric can be called in different ways depending on the properties of the two forms, depending on the closeness of omega with respect to several differential operators. So the most important one is the Kähler property. So omega is called Kähler if it is closed. So if d omega equals 0, d here stands for the usual differentiation operator. But we can relax this condition in several ways by asking the closeness of omega with respect to some other naturally defined operators. So also some other metrics that you learned about in some other courses can be defined in similar ways, like omega is called balanced if omega, instead of being closed as for the Kähler condition, is co-closed. So d star of omega is 0. Here d star is the adjoint of the usual exterior derivative with respect to the metric G. And in a similar fashion, another intensively studied metrics, kind of metrics, are pluriclosed metrics. Also known as strongly Kähler with torsion. And these metrics are those metrics for which the fundamental form is d bar closed. So if d bar of omega equals 0. So here I denote by d and d bar the two components of d. So as you already known from complex geometry course, the exterior derivative splits as the sum of d plus d bar when this del operator sends pq forms in p plus 1 q forms, and d bar is the part of d sending pq forms in p q plus 1 forms. Okay, so definition 2 and definition 3 are clearly generalization, relaxations of definition 1. So beware that definition 2 is also is equivalent to the closeness of the n-1 power of omega. So omega being co-closed is equivalent to omega to the power n-1 being closed. So these kind of relaxations of the first condition appeared naturally since Kähler metrics are quite rare, so to speak, in the world of complex geometry. So asking that omega is closed is quite a powerful condition. Okay, and coming now to the object of this course. We shall call a metric omega locally conformally Kähler or shortly LCK, if omega satisfies this equality, the omega, instead of being 0, is theta wedge omega, where theta is a one form, real, and closed. So this one form, theta, is called the Lie form of the metric. The Lie form of omega. Okay, a very natural question is why this definition 4? Because obviously it is different from definition 2 and definition 3. So from balanced and pluriclosed metrics, since in the balanced and pluriclosed condition, omega was closed with respect to some more friendly operators. So arising only from the exterior derivative and the metric itself. So how come this might be an interesting object, asking omega to satisfy this kind of equality, the omega equals theta wedge omega, where theta is a closed one form? Well, to begin with, the advantage is that definition 4 is conformally invariant. So from the point of view of conformal geometry, this definition would be the next best thing of a Kähler metric. So by conformally invariant, I mean that if omega 0 is LCK, then any other metric conformal to this one is again LCK. So omega 1, which is a positive factor, positive function multiplied with omega, is again LCK. And indeed, one can see this just by doing a trivial computation. If we take the exterior derivative of the exponential of f multiplied with omega 0, this is the exponential of f times d of omega 0 plus the exponential times df wedge omega 0. And therefore, taking into account that omega 0 itself is LCK, so d of omega 0 is theta 0 wedge omega 0. In the end, we get it's theta 0 plus df wedge omega 1, since this new metric was baptized omega 1. Okay, so it means that any conformal metric to an LCK metric is again LCK, and the newly form changed by an exact factor, changed by adding this d of f. So in other words, it means that the correct term would be not necessarily an LCK metric, but an LCK structure. So an LCK structure would consist of the conformal class of omega of the metric, which comes along with the cohomology class of the Lie form, but the whole cohomology class. Because as we have seen in the previous computation, the conformal metric has as associated leaf form the original leaf form that was theta 0 modified by some impact factor. So this would be an LCK structure, the conformal class of an LCK metric and the associated the RAM cohomology class of the leaf form. Okay, so in a sense, LCK metrics correct a small defect of Kähler metrics, which is the fact that a conformal metric to a Kähler metric is not Kähler if the conformal factor is not constant. So if omega is Kähler, then this conformal metric is Kähler if and only if f is constant. So this would be the reason why I said the definition of LCK metrics is quite natural from the point of view of Kähler geometry. This would be a natural generalization of Kähler metrics. Now, a couple of useful remarks. The first remark is that we have an equivalent definition for LCK metrics, which tells us that they are exactly what their name says. So an LCK metric has the following equivalent definition. Which I will call definition 5. So a metric omega is LCK if there exists a covering with open sets of the manifold M, and there exist some smooth functions on each of these open sets, such that omega multiplied with some suitable conformal factor is Kähler on each of these patches. So of course, I consider, so a metric omega means that omega is already Hermitian. So a Hermitian metric omega is LCK if there exists an open covering and there exists some local functions that are smooth, such that omega multiplied with the exponential of these functions is Kähler on each open set UI. Okay, let's see that this indeed is equivalent to definition number 4. So let's do the easy implication. Definition 4 implies definition 5. So if we know that the omega is theta wedge omega, the most natural choice for this open covering will be to take the open sets where theta is exact. So since theta is closed, there exists an open covering of M such that theta is exact when restricted only to this open set. And the primitives, of course, are smooth. Then it's just a matter of a small computation to see that the exponential of minus fi, so the primitive of theta restricted to the open set UI times omega is scalar on every open set, right? Because we just have to check that this is a closed form. And it is. Always using the fact that the Fi is precisely theta and the omega is theta wedge omega. So this is 0. There is a minus missing. The other way around, if we know that such a covering exists, we have to recover the fact that the omega equals theta wedge omega. So now we know that the exponential of minus Fi times omega is scalar on each open set UI. So therefore, we know this is a closed 1-1 form. Therefore, we know that d omega is equal to dFi wedge omega on the open set UI. Okay, but this is something we can write on any open set part of this covering. So let's see what happens on the overlap of two intersecting open sets of this covering. So at the same time, we know that the omega is dfj wedge omega on uj. So here, we know that dfi wedge omega is equal to dfj wedge omega. But a simple linear algebra fact that tells us that wedging with a non-degenerate form is injective applied to one forms. So this is injective. This is something you have to check locally. You have to check it pointwise. It's just a matter of linear algebra since omega is non-degenerate. Therefore, we get that dFi on the overlap is equal to dfj on the overlap, right? Because this equality here was an equality happening on the intersection between ui and uj. So therefore, these exact forms that are local will glue up to a globally defined closed one form. To a closed one form theta. So now we have that these local relations here, the omega is equal to d of fi wedge omega, amount to a global relation. So we can say that globally the omega is theta wedge omega. And therefore we have our equivalence between the two definitions. And this is a nice definition because it says exactly what the name means. It is a form that is locally conformal to a Kähler metric, to a Kähler form. Okay, now if we take a better look at this equality that d omega equals theta wedge omega, and if we want to put the definition 2, definition 3, definition 4 in a more unified frame, we can say that also this equality amounts to the closeness of omega with respect to a new operator. So if we twist the exterior derivative with theta, so if we define this new operator called d theta equal to d minus theta wedge. So this is an operator which increases by 1 the degree of the forms. Then we can say that omega is LCK if omega is close to the operator d theta. Okay, this is just a matter of renaming things. But the interesting part is that theta being closed amounts to d theta squared being equal to 0. So if we look at this complex, that is the Durham complex, but modified with d theta, so twisted with this d theta. This complex, so this is first of all, this is a complex because d theta squared equals 0, but this means it has a cohomology, so we can define some cohomology groups associated to this operator, and these are usually denoted by h theta. So h theta of a generic index, the manifold M, which is of course the kernel of d theta quotient to the image of d theta. This is something called the Morse-Novikov cohomology. Of the manifold M with respect to theta. And I will come back to this cohomology later in a future course. So obviously, in the LCK setting, this cohomology is an interesting object to study and a natural one. Okay, now two trivial observations that I should have made earlier are that if theta is 0, then omega is scalar. And let's say this is the most boring case. We don't want to study LCK metrics that are Kähler. We are interested in genuinely locally conformally Kähler metrics. And another boring case is when theta is globally exact, and then omega is called globally conformally Kähler. So in the sense that it can be rescaled to a Kähler metric. So since the omega is df wedge omega, then a simple computation will show you that the exponential of minus f times omega is Kähler. So a manifold admitting a globally conformally Kähler metric is Kählerian, is of Kähler type, admits a Kähler metric, this one, e to minus f times omega. Okay, so let's say that from the point of view of LCK geometry, we are interested in the case when theta is not globally exact. So when the cohomology class, the Durham cohomology class of theta is not 0. Still, there is an interesting way to link LCK geometry to Kähler geometry. And for this, we need to understand the following point. We need to understand the universal cover of an LCK manifold. So we need to understand that this universal cover has very special, very particular features. So let's take the universal cover, usually denoted by n tilde, and the covering map pi, and assume that M is LCK. So on M, we know that we have a Hermitian metric omega satisfying the omega is equal to theta wedge omega. Now, what happens if we pull back the Lie forms data to the universal cover? Since the universal cover is simply connected, then this pullback is a globally exact one form. So it's the differential of a globally defined function f. By defining now omega, let's call it maybe better omega tilde, on the universal cover to be the exponential of minus f times the pullback of omega. So this is undoubtedly a Hermitian metric. This is Kähler. Again, it's just an easy computation for you to see that omega tilde that has defined is closed. And moreover, omega tilde has some interesting property besides being Kähler. And the property is that it is homothetized by the fundamental group. So I mean by this, if we take any element in the deck transformation group, which is anyway an instance of the fundamental group of M, then the way gamma acts on omega tilde will be by multiplying it with a constant, with a positive number. So the universal cover has a Kähler metric that is homothetized by the deck transformation group. So why is that? So this is because if we write down with the pullback of omega tilde via gamma, so this is gamma star of e to the power minus f times the pullback of omega, which is the exponential of minus the pullback of f times the pullback via pi of omega. So this is because gamma is a deck transformation. And now if we do this trick to reinsert the exponential of f, so this is the exponential of f minus gamma star of f times omega 1. So this is omega 1. Okay, but this element here is precisely e to the power minus the integral of theta on the path gamma, because gamma is a deck transformation, but can also be seen as an element in the fundamental group, because the pullback of f minus f is the integral of theta along the path gamma. So this is a positive constant. This is C gamma. Okay, the other way around works too, and this is what we will follow, what we will prove. That if we have a manifold whose universal cover admits a Kähler metric that is homothetized by the deck transformation group, then the manifold admits an LCK metric. So if the universal cover admits a Kähler metric omega such that gamma star of omega is a positive number times omega, then M admits an LCK metric. Okay, the little difficulty in proving this proposition is that we need somehow to manufacture the Lie form on M. This is the difficult part. So the strategy is to fabricate somehow the Lie form. To think from what of this, from which ingredients that we have here, that the Lie form arises. And this is because we have, since we have this positive number associated to any transformation, to any deck transformation, we can recover from this a cohomology class in the first Durham cohomology group. So to any deck transformation, we can associate the logarithm of this positive constant. So this is something we are allowed to do since C of omega is positive. So this assignment gives us an element in the dual of the fundamental group. Right, so I always think of the deck transformation group as being isomorphic to the fundamental group. And who is the dual of the fundamental group? It is precisely the first Durham cohomology group. So if you want to see how we want to see this isomorphism from the direction from right to left, so to a cohomology class, we will associate the element gamma goes to the integral of theta along gamma. Okay, so now we have out of the data, out of gamma and C gamma, we can recover this cohomology class in H1 Durham. So take now any representative of this cohomology class. Okay, any representative that we will call theta. Then the pullback of theta again has to be globally exact on the universal cover since it is simply connected. So it is the differential of some function. By taking now the exponential of this function multiplied with our Kähler form, let me see if I denoted it by omega or omega. I denoted it by omega. Okay, this differential, let's do the computation. Since d omega is 0, because omega is Kähler, what we get is the f wedge f times omega. So let's call this new form omega 1. What we have is that omega 1 is a 1-1 form, is a Hermitian metric such that d of omega 1 is equal to the pullback of a closed one form wedge omega 1. We would like to prove that this omega 1 is pi 1 invariant, so it descends to M. This way, the metric to which descends to will be our LCK metric with Lie form theta. So we want to prove that omega 1 is pi 1 invariant. And therefore it descends to M. Well, to check that it is pi 1 invariant, we just take deck transformation and do the computation gamma star of omega 1. So the exponential of f times omega is the exponential of gamma star of f times gamma star of omega. Gamma star of omega, we know that is a positive multiple of omega, which is c omega. And we can introduce artificially the exponential of f. This is again omega 1. And since the constant c of omega was exactly the exponential of the integral of theta along the path gamma, we get that this element here, this function here is precisely 1. Therefore, omega 1 is indeed pi 1 invariant and comes from a 1-1 form downstairs. So therefore, omega 1 is the pullback of a form omega 0 on M. And therefore, the omega 0 is just theta wedge omega 0. So M is LCK. Okay, so this what we learn is that an LCK structure on M is equivalent to a Kähler metric on the universal cover such that gamma star of this Kähler metric, omega tilde, is a positive multiple of omega tilde. And this will be our main tool to build LCK metrics on manifolds. We will build actually Kähler metrics on the universal cover that have this property, and therefore we will deduce that the manifolds that we are interested in carry an LCK metric. Okay, so now I will finish the first lecture by giving an explicit example of an LCK manifold. So maybe the easiest example would be the diagonal Hopf manifold. So the diagonal Hopf manifold is a quotient of Cn minus the origin to the cyclic group generated by an automorphism given by the multiplication with a real number different from 1 or minus 1. So this F is just the multiplication with whatever we want different from plus minus 1. So F of Z1 Zn is, say, 2Z1 2Zn. So I could have written that is Cn minus 0 quotient to Z goes to 2Z. Okay, so in this way, we can see that M is actually a quotient of Cn minus 0 to the action of Z. So the fundamental group of M is actually Z. Differentiably speaking, so as smooth manifold, this M is nothing but the product between S1 and S2n minus 1. This is just by seeing that Cn minus the origin can be understood as R plus times the 2n minus 1 sphere, right? So this R plus takes just the norm of the vector, and the S2n minus 1 part takes the unit vector that gives the direction. So this is the correspondence. Z1, Zn goes to the norm of Z, and the unit length vector given by dividing with the norm. Okay, so now we have a manifold that we understand very well. We know that the fundamental group is Z. We know that the universal cover of M is Cn minus 0. So M tilde is Cn minus 0. And we would like to deduce somehow that M is indeed LCK. This would be the easiest example. Well, we will use the previous proposition. So if we take any gamma in the deck transformation group, so any gamma in the pi 1, so in our case, gamma would be just power of the automorphism F. Then gamma acts on the standard Kähler metric on Cn minus 0, which would be, so let me just write here omega 0 to be the standard Kähler metric on Cn minus 0, which is I d Zj with dZj bar, the sum from J to 1, from 1 to n. So gamma star of the standard Kähler metric is just a constant. It's not important what the constant is. It's important that it is a constant. So it is this power of 2 times the Kähler metric. Okay, so by the previous proposition, the diagonal Hopf manifold, so our M is LCK, because the universal cover has this Kähler metric that is homothetized by the transformation group. The LCK metric on the Hopf manifold can be seen easily in coordinates above. So the LCK metric on M is, let's call it omega 0, such that the pullback of omega 0 on Cn minus 0 is equal to the sum of dZj wedge dZj bar divided by the norm of Z1 Zn. So the norm of Z squared. So this is the pullback of the LCK metric. So one can easily see that this form defined on Cn minus 0 is pi 1 invariant. So it's invariant to the action of F. And moreover, the differential of the pullback of omega 0 is, if we do the computation, is the differential of 1 divided by 1 over the norm, the norm squared, wedge the standard Kähler form, so if you want to introduce now the artificially the omega 0, so we divide here by the norm squared, we multiply again with the norm squared, we get that the differential of the pullback of omega 0 is equal to the derivative of 1 over the norm squared divided by 1 over the norm squared wedge the pullback of omega 0. So it is minus d of the logarithm of the norm squared wedge the pullback of omega 0. So this form here is the pullback of the Lie form. So only by looking at it, we can see that this form is pi1 invariant, because if we act with the f, if we act with the gamma, which is the power of f, any gamma, this is invariant. Okay, so it means that the omega 0 is indeed omega 0 wedge omega 0. So the diagonal Hopf manifold is the easiest example of LCK manifold. And in the next lecture, we will see more elaborated examples and exactly how we will construct the Kähler metric on the universal cover by a Kähler metric that has this property that pi1 acts by multiplying the metric with positive constants. Okay, so see you next time.